So welcome everyone. So if you all think AI is just hype, so you are about to see why it's more than that and why it's so crucial for cloud native. And if you're already on board, buckle up because we're going to be diving into the cutting edge future fusion of cloud native and AI and see why it's shaping up the future of our ecosystem going forward. A little bit about us. My name is Nikhita, and I work at Broadcom. I'm also the vice chair of the CNCF Technical Oversight Committee, and I'm also one of the chairs for KubeCon.
Hi, and I'm Rajesh. I work at Broadcom too. In the cloud native community, I am a tech lead for CNCF Technical Advisory Group Runtime, and I also happen to be one of the co-chairs for Cloud Native and Kubernetes AI Day, happening in Salt Lake City later this year.
So y'all must be knowing a little bit about AI already, but we'll still talk about it with some graphs because they're pretty. So to start with, according to McKinsey's State of the AI Report 2024, we can see that companies have adopted AI in at least one business function, and this adoption has surged dramatically in the past year, and you might already have seen it with how much we're talking about AI in all of the conferences recently. And we can also see that 54% of the organizations are now running their AI and ML workloads on Kubernetes. Now, this explosive growth is very exciting, but it also highlights one very important thing, that we need to start thinking about what it means to support these workloads on Kubernetes and what needs to be done more to get to that point.
Yeah, I think AI is more accessible than ever right now, thanks to ChatGPT. And here's a quote from Jeremy Howard. Jeremy Howard is a co-founder of a AI research lab called Answer.ai, wherein he compares AI to the internet of the 90s, right? And he further goes on to say how the research shows that any area that is picked up by deep learning eventually becomes state of the art and goes well beyond what people thought was possible, right? And I think this is just the beginning of the era. Currently, AI has been applied to, say, text, image, or voice data. So there's a lot more to come. One fundamental thing, though, is the internals of the AI become like a black box for us. But as builders of the platform that runs AI, we should be able to know all of these moving pieces, right from the data sets that make up these models, to the metadata that goes into building these models, to how these models run or serve and get deployed for inference. It's important that we get into the fundamentals of each of these steps. Only then can we build platforms which are robust to support AI workloads. Currently, a lot of topics in the cloud native ecosystem have kind of become rinse and repeat kind of a model. They kind of seem deja vu. And AI becomes that niche area which kind of brings up interesting, cool problems. I think we should change our perspective of not treating AI as just hype, but instead trying to solve the problems that it comes with.
Yeah, so when Kubernetes was first designed, AI was such a niche area of adoption, and it's probably feels like it's true even now. But from the data, we've seen that that's not the case anymore. AI is everywhere. And while platform engineering has emerged as a very hot topic recently, we can see that AI is bringing some more thrill into the ecosystem with cool problems. And that's also making us question how much we can stretch Kubernetes to support AI workloads. And all of these efforts have now led to a new star being born in the cloud-native universe called DRA, or Dynamic Resource Allocation, which is a new feature in Kubernetes. So to learn more about what's DRA, let's look at the current state without the feature being enabled. Now, with the device plugin API, so the system hardware resources need to be, with that we can advertise the system hardware resources to the kubelet. This also means that instead of updating the code in Kubernetes itself, vendors can now use this device plugin API and have targeted devices like GPUs, FPGAs, high performance NICs, and other computing resources that basically need some sort of vendor initialization and setup. But with AI infrastructure in mind, there are some limitations with this approach, so let's see what they are. So first is device initialization. So like if I'm starting a workload that uses some sort of an accelerator like GPU, I should be able to have the accelerator reprogrammed or reconfigured without needing to redeploy or deploy my application with root privileges, because we really don't want to do that. But today, it's not possible to specify like the desired device properties that are required for reconfiguring devices. And the second one is device cleanup, right? So if a workload is finished, I should be able to have a mechanism to clean up the device. But today, post-stop actions are not supported. And thirdly, the most important one, there is no API to request for partial device allocation without DRA, right? So with the device plugin API, devices need to be pre-partitioned, and they need to be advertised the same way of full or static devices. So then I, as a consumer, will need to select from the list of predefined devices. So it puts the burden on me to select the right device type. But with DRA, it's possible to solve all of these problems because it allows to declare the resource constraints more abstractly. And the fourth one is that currently there's no way to specify like soft or optional allocations. What this means basically is like if a device exists and it can be allocated, then it should be allocated. But if it does not exist, then I should be able to run a workload on a node without a device. For instance, I should be able to fall back to using only CPU if a GPU is not available. Now, the DRA feature helps solve all of these problems, but the DRA is not meant to replace the device plugin, right? So the device plugin has its own merits, and for use cases that don't require dynamic allocation, it's good enough, right? So both can coexist together, and it's also important that it does so that we don't break the stable APIs. So let's take a slightly deeper look into what DRA is, but we won't go into too much detail. So DRA is alpha in Kubernetes 1.26, but it went through a big revamp in Kubernetes 1.30. It can be enabled using the dynamic resource allocation feature gate. And it also introduces some concepts like resource slice, device class, resource claim, and so on, but we'll see what they are. So let's start with device class. So if I'm a cluster admin and I want to make GPUs available to the users of a cluster, I create something called as a device class. So that can include some parameters that I as a cluster admin can choose. For instance, I can specify a command with root privileges that can do some sort of cluster-specific initialization of a device every time it's prepared on a node. Now, let's look at a resource slice, right? So we have some devices, and we want to publish these devices on the node to the API server. So I then create something called as a resource slice. So resource slice, as you can see, it's essentially like a set of collection of devices of which we can allocate resources. Next, and the most interesting thing here is that we can define some sort of shared capacity, right? So that can be consumed by one or more devices that are there on the node. So this also means that you can declare shared capacity for a set of memory blocks in a GPU, as you can see here. Now, similar to a persistent volume claim, you can create something called as a resource claim, which can then be referenced in a pod. Can you go to the next slide? Yeah, so we can reference this in a pod. So this essentially means that we can have two containers in a pod that can share the same subset of GPU, which is exactly what we're looking for, and this can be achieved through DRA. So you can also try this out yourself using the upstream Kubernetes upstream DRA example, this URL, or the ones that NVIDIA has published. Also, there's a lot of effort going on to make this feature beta, and there's been a lot of requests to make it to beta. So if you'd like to join in on the fun, please contribute to Signode and read the DRA cap. It's a beautifully written cap with a lot of examples and goes into the slide internals of Kubernetes, which gives a very good comprehensive overview of how all of this works under the hood.
Yeah, now that we've looked at how Kubernetes is trying to tackle this problem, let's also look at some of the other projects in the cloud native ecosystem, which are trying to democratize access to AI infrastructure. All right, so how many over here have heard of Kubeflow? Can I get a show of hands? Cool, yeah, that's a sizable amount. Kubeflow is basically a machine learning toolkit based on Kubernetes. And they had a user survey in 2023, which kind of pointed out that 44% of the users wanted model registry as a feature. Model registry is basically a store of models and metadata and versions for AI consumers just to produce or push and pull models along with their metadata and versions and so on and so forth. Why this has become such an important ask, in order to understand that, we need to look at what was the problem over here, right? So currently, yeah, cool. So currently, this is the current state, right? Like in the cloud native ecosystem, we do not have a model registry store, which stores or which kind of has models along with their hyperparameters associated with a particular version. So it is difficult to track what is the metadata associated with version 1.0 of a model as compared to version 2.0 of a model. What this means is, consider a persona over here of an AI engineer. They want to evaluate the performance of a particular version of a model as compared to the other version of the model, and the only diff over there can be how the hyperparameters differ. So they are kind of caught up in a fix, because then the onus is on them to track all of these metadata. This also puts MLOps engineers in a miserable state, because now they have to pull the latest version of a model with the right configuration in order to deploy it. So this is exactly where Kubeflow is trying to solve this problem. Next slide, please. Yeah. With a structured artifact where the metadata and the version is tightly coupled with the model. Once you have this, you kind of get a catalog of models wherein you're able to manage versions of different models for deployment in different environments. This is what Kubeflow is trying to do in its model registry workstream. This is a snapshot of how easy it is to register a model in Kubeflow's model registry workstream. This is a snapshot from their documentation, wherein you can clearly see you specify the URI of storage location of the model, along with whatever is the hyperparameters and the version aspect of it. And all of this is kind of succinctly put in order to register it, and then anyone who wants to retrieve it can also do it in a similar way. Can you go back to the previous slide, actually? So the other thing to highlight over here is this metadata is in an MLMD format, which is basically machine learning metadata format, which is a project meant for storing and retrieving metadata for machine learning models. And the model registry project is kind of built on top of the MLMD project. Yeah, so there's active development happening in the Kubeflow model registry workstream. Maintainers are trying to explore OCI spec as an infrastructure layer for the registry aspect. What that gives is things like artifact signing, RBAC policies, so on and so forth, right? And I think this is crucial because these are the goodness that we get from cloud native best practices, which kind of help tackle problems which are faced by the AI community.
Cool. So let's talk about taking AI the edge. So the WASM project in CNCF has been making amazing strides with LLM inference across both CPUs and GPUs. So let's see what this means. So if a developer creates a LLM inference application, say using PyTorch on Windows and NVIDIA 4090, and they want to deploy it to NVIDIA 810G server on AWS, they're going to run into several issues. Starting with PyTorch, it has a lot of complex dependencies and it's not completely lightweight. And even if the developer builds this in a container on their own machine, it's still unlikely that this will run on the server on AWS because the architecture version may be different or the CUDA version may be different. Next, the second problem with GPUs is that up until now, we've been mainly looking at few types of CPUs. But with GPUs, we have tens of types of GPUs. So the issue of rewriting, recompiling, and retesting gets amplified with machine learning, right? And again, like lightweight containers are not the solution here because with that comes the additional overhead of installing drivers and other dependencies. So enter the WASM Edge project. So it's a CNCF project that is a lightweight and portable AI and LLM runtime. It currently supports Rust, but JavaScript is also almost there. So what it means is like you just need to call the WASM Edge API to perform inference operations. So you don't need to worry anything about GPU drivers or tensor libraries or anything like that. So what it does behind the scenes is it compiles your application into WASM, and then you can redistribute or deploy the WASM binary files using the existing tools that you all are pretty familiar with. And you can try this out using a one-liner demo. So what it basically does, it installs WASM Edge, it downloads a LLM, and you can basically run this LLM and chat with it without any internet connection. So let's try it and see how that goes. Okay. Let's see. So I'm just going to run that one-liner command. So this is going to fetch WASM Edge from GitHub. May take a while. Okay. It's running.
And we had also cached the LLM so that we save some time on that. So we've kind of cached the model over here. And I think now it starts the chatbot web application.
Yeah, it's pretty fast that way. So now we have that. And I'm just going to reload this. So we have an LLM here, and you can talk to it. Say something like, who am I talking to? And
yeah, pretty cool for something without internet access.
Yeah, and then you can just continue working with this LLM, just chatting with it without any internet connection. So this is how you can try it out right now, or just before you leave the conference and see and play around with it. Okay, let's go back.
Yeah, I think now let's talk about observability because you can't run LLMs in production without observability. It's difficult to debug LLMs, especially when the output generated by an LLM is factually incorrect. And while debugging, there are a lot of aspects which go into it, which is mostly around what went wrong, why it went wrong, is the fix worth the effort, would the fix cause regression of something that has already been working before. So to consider all of these aspects, let's try to look into what observing LLMs means. To start with, there's something called as request information, which is basically an API call to the LLM. This can be like a API call to a publicly available LLM or a self-hosted one. Next, large language models can be considered as chains of blocks, wherein output of one eventually goes to the other one. Prompts is another big one because it depends on the size of the prompt, the output requested, so on and so forth. Latency is basically from an end user perspective and again depends on the prompts as well as the output. The data that's involved in all of these interactions is high cardinality because it's natural language processing, inputs, outputs, versions, and so on and so forth. So there are a lot of other aspects to it, and these are only some of which we have highlighted over here. But the point that I'm trying to notify over here is if you zoom out, these are some of the problems that have been solved by database folks, right? There are standardized instrumentation techniques around this. So it's up to us to take inspiration from how database folks have already solved these problems. And what I want to highlight right now is the project Open Telemetry, which is trying to standardize LLM semantics in its own way. And it's trying to do that with best practices for observing LLM applications. This involves how to debug LLM, standards around it, what it means to evaluate LLM performance. This may mean the accuracy of the response, what is the user feedback like, and so on. It also is trying to highlight the operational costs around the API calls and so on and so forth. And most importantly, trying to propagate ethical use of LLMs in terms of privacy compliance, bias detection, which are really important when it comes to using a large language model. So talking about AI safety, I think it's time to take a moment to step back and take a zoomed out look at the ecosystem. So what we have over here is what Kubernetes offers to AI workloads, right? It offers scalability, efficiency, portability, fault tolerance to basically train, fine-tune, deploy, and run AI workloads for inference. On the other hand, next slide, please. On the other hand, AI opens up the horizon for cloud native in terms of tools which can predict potential issues with your Kubernetes clusters, LLMs that can generate configurations for your clusters, or a combination of predictive as well as generative AI, which can help scan vulnerabilities and so on and so forth. So the usage of AI is only going to increase in the intersection of cloud native and machine learning and artificial intelligence. So at this juncture, we should take a look at what it means to use AI responsibly. With such a large-scale use of AI, the pitfalls will be high stake as well in terms of failures. And as builders of software that runs AI, it is our responsibility to learn how to consume and produce AI responsibly. So to understand what responsible AI means, we should focus on concepts like contestability. So what this means is artificial intelligence models should be able to explain their outputs to humans or to other AI systems in order to protect, say, human rights, right? To protect human rights, they need intervention from humans at every stage of the life cycle. So that's contestabilities. There's like a lot of research happening in this area. It's called contestable AI. There are multiple research papers around this. So the research community is kind of focusing on this aspect. The other big one is bias, and that stems from the data being used by the model. And your model can be as good as the data it has been trained on. So to focus on bias, I would like to highlight this project called Gender Shades by Timnit Gebru and folks. And what they did over here is they took a bunch of AI products which were focused on humans, and they evaluated that based on the performance on different types of humans. What they found out was these products performed worse on women and worst on people with dark skin. And this kind of highlights how the difference between, say, a traditional software build and something like a machine learning model is the data set that it's being trained on, right? We need tools which can backtrack to the malicious data that eventually led to a false positive output of the model. And this kind of brings us to software supply chain and attestation and all of the cloud native best practices which we can use to make this better. What we need is AI supply chain or AI SBOMs, which can tell us where a model was trained on, where is it deployed, how was it trained, what data was it used on. And with all of this information, we'll be able to this is another interesting blog post by Adolfo, which kind of focuses on supply chain and software, supply chain as well as AI S-bombs on how to make AI more transparent and more secure and reduce bias. To sum up, I would like to focus on this quote by Rachel Thomas, who is co-founder of Fast.ai and also an AI ethics researcher. And I really like the emphasis on contestability, justice, and how power should be given to people who are impacted by AI systems.
So after all of this, if you are now convinced that now is the right time for Cloud Native to focus on AI, we also have a AI working group in the CNCF that you can join using this link. So the working group has released a white paper that talks everything about this. So it starts from the beginning of what it means to run AI workloads on Cloud Native. What aspects do you need to consider? Where are we at in the current state today? What is the desired state? What do we need to get to that desired state? It basically outlines all of the challenges and opportunities in the space. So the working group is a really good place to get into if you are interested in this topic. Another deliverable of the working group is the Cloud Native and AI landscape, which basically gives a view into the ecosystem for all of the CNCF projects or the projects in the Cloud Native ecosystem, really, that are working on this. So they don't have to be specifically AI-related projects, but more of like for example, open telemetry, right? So it's an existing CNCF project that's doing work to support AI workloads. So this landscape will give an overview of this, and like if you want to get involved or learn how the ecosystem is shaping up, this is a good place to know that. And finally, what we are working on right now is a playground where beginners can play around with running AI on cloud-native infrastructure. So this is still very early stages. So if this is something that you're interested in, please go to this GitHub issue and drop some of your ideas, concerns, or comments, and we'd love to hear more from you. So with that, thank you, and I hope this session was valuable to give some sort of an overview of what the space looks like and why you need to start thinking about cloud native and AI now. Thank you.
Thank you so much.
Thank you so much. So we are at the session time. We have two questions that you can see on the screen. The first is, AI clearly has bright future ahead. Is there a way for AI to reduce the resource consumptions for AI workloads on Kubernetes, making them more efficient? What do you think?
So that is exactly what DRA is about, so the dynamic resource allocation feature that we talked about. So since it has some sort of shared capacity, or you can say that, okay, this is this GPU, but I want to consume just like 2 GB of it, and then there's another container that wants to consume 3 GB. So this happens all dynamically, so right? So you aren't essentially wasting space, and you're efficient with the resources that you have in store.
Thank you. And the last question that we have so far is, how is Kubernetes suited for real-time processing of AI workloads? Does it allow for elasticity and dynamic scaling?
I think more from Kubernetes, there's a project called Kserve, which is trying to solve this problem in terms of deploying AI workloads and how they can be scaled, how they can be served better. So I think that's like the project that I would say that's more focused on this area.
Thank you very much. One question is coming up. Okay, the question was, so the slide will be shared after the conference, so no worries about that. Actually, if I can ask one question myself regarding all this AI stuff is, what's your thoughts about helping developers running and managing Kubernetes day by day? Do you really think, or to say differently, how do you think AI can help developers in making their Kubernetes platform more efficient, more stable, and more secure?
I think yes. There's not a lot of innovation happening in that space, but I think we need to focus on that area more in terms of Kubernetes spits out a lot of logs, right? Like a platform which is based on Kubernetes would give you like a lot of audit logs, and machine learning models are good at analyzing all of those logs, and then predicting potential failures or potential vulnerabilities or potential disasters that may happen to the cluster. I think from a CV scanning operators or from making your platform more robust, we should focus on innovations around building these models, wherein you take this data and kind of train some models which can analyze and help you better and kind of leads to better productivity and eventually makes a cluster more resilient.
Also, similar to ChatGPT, since everyone's heard of it, there's a project called Kate's GPT that's already part of the CNCF that looks at like your error messages and suggests what's wrong and helps you debug and troubleshoot further. So there's a lot of work happening in that space, but it's again, like Raju said, it's very early stage and there's a lot more to do there.
Thank you very much. One last question then. Which particular APM tool would you suggest to use along with ODL agents to get better insights on LLM workloads?
I'm not sure I get this question. Maybe we can take it in the hallway track later on.
I think the idea was, so there are a lot of APM tools that exist in the ecosystem. So what's your thoughts on this APM tools related to AI and to observe LLM workloads? Do you think this will come up a certain time or?
There's a lot of proprietary ones, I think, coming up. So OTEL is still also very early stages. Like there was a working group formed recently, and they're still talking about what are the semantics associated with observing AI workloads and so on. So I don't think we're at that maturity where we have a lot of tools available, but I think there's still work going on in the space. So
yeah, I would still bet on OTEL at this point.
Thank you very much. Thank you very much for this very interesting talk. Please give them a big round of applause.